Hi, welcome to the Arcade School. I'm Randy Fromm. In this lesson, we're going to be taking a look at switching regulator power supplies. Here are some typical switching regulator power supplies. And as you can see, they come in a variety of different colors. There's a gold one and a red one, a black one, and a gray one. There are green ones, there are silver ones, all kinds of different colors. Does the color really make any difference? Well, no, not really. In fact, not at all. Inside these power supplies, they're almost all exactly the same. These power supplies are commonly referred to as the Peter Chow type of power supply, named after one of the early engineers that designed this power supply for video games. In fact, this one happens to be a Peter Chow power supply manufactured by Peter Chow himself. Well, let's take a close look at the switching regulator power supply and see how it operates. These two terminals are used for the 115 volt AC input. This is obviously the same AC input that powers the entire video game itself. Right next to the 115 volt AC inputs is a terminal marked FG. FG stands for frame ground, and this is where we connect the earth ground, the green wire that connects to the little round pin of our AC power distribution system. Although a switching regulator power supply will work perfectly well without the frame ground terminal connected, it's a good idea to connect FG to the earth ground itself. As these power supplies operate, they can generate a certain amount of electrical noise. This electrical noise can show up as bands of interference on the video game's monitor. By grounding the frame ground, that interference can be minimized or eliminated altogether. Naturally, the power supply has output terminals as well, and the output terminals are marked +12, -5, ground, and +5. Well, let's take a look at it and see what's inside. It's pretty easy to open up a switching regulator power supply. There's only 6 screws to pull the top off of it. 4 of these screws are used to hold the heat sink in place, or the heat sinks actually, as there are usually 2 of them. We'll talk more about heat sinks later on, once we get the thing open. Then there's 4 screws, 1 in each corner, that hold the actual cover in place. I suppose I should have an electric screwdriver, but I like to do things the old-fashioned way. It does help to have a magnetic screwdriver, however. Once we've taken the screws off, we can lift the cover off, just like this. And in fact, we can remove the cover completely. And here's the board itself. To pull the board out, we'll just raise it up out of the box like this. Now, just so that we can take a close look at it here, I'm going to install a couple of the screws back on it and put them in the corners so that the board will stay up above the case and we can take a better look at it here during this lesson. Put 1 in each corner. Of course, normally you won't have to do this while you're actually doing the repair. And now we can actually take a look at the inside of the board itself. The 115 volts AC enters the power supply and first passes through a fuse. This fuse is generally rated at around 2 amps. After passing through the fuse, the AC power is then passed through something known as an AC line filter. The AC line filter is used to remove any electrical interference from the power supply, interference that might get out of the power supply and get into your video game monitor. The AC power line filter may look like this, or you may see a filter that looks like this. This is just a small plastic case that covers the filter. Inside, they both look about the same. You will also see a cluster of small capacitors surrounding the AC line filter. The capacitors also help remove any electrical interference from the power supply power line. Again, interference that may get out of the power supply and affect the picture that you see on your monitor. After passing through the AC line filter, the 115 volts AC is then passed to a bridge rectifier. These bridge rectifiers come in a variety of different shapes and sizes. You may see round bridge rectifiers, you may see rectangular or square bridge rectifiers, or you may even see a bridge rectifier that's made of 4 individual diodes. Regardless, they all work the same way. And in fact, we're actually only using 2 of the 4 diodes. In Europe, where they use 220 volt power, they use all 4. But here in the United States, where our power is only 115 volts in, we use actually just 2 of the 4 diodes. The diodes in the bridge rectifier take the 115 volts AC input and convert it into DC. Actually, they convert it into 2 different DC power supplies. One is about plus 150 volts DC, and the other one is the opposite polarity, about minus 150 volts DC. After passing through the bridge rectifier, the DC is then filtered by a pair of filter capacitors. It's real easy to recognize the high voltage filter capacitors. They're the only 2 high voltage capacitors in the power supply. They will generally be rated at around 200 volts DC. This plus and minus 150 volt power supply, which is known as a split supply, is then passed through a pair of switching transistors. The switching transistors are mounted right here on this heat sink. I'll have to take this cover off, or this clamp that holds them against the heat sink, so that you can take a close look at them. There's only a single screw that holds the cover in place. Once I remove the screw, we'll be able to see the 2 switching transistors themselves. And here they are, mounted on the heat sink. You'll also notice that there's a small insulator behind them. The insulator is very important. If you ever replace these transistors, you must make absolutely certain that you replace the insulator as well. Remember, the metal tabs on these transistors are the collectors themselves. And as such, they're electrically hot. They'll have plus or minus 150 volts on them. So be quite careful. Make absolutely certain that you replace this small insulator before you install the clamp or the cover back on the transistors. These transistors are used to alternately switch the plus 150 and the minus 150 volts across the power transformer. Here's the power transformer. It always sits right in the middle of the power supply, and for some reason it's always yellow. This power transformer takes the place of this very large iron core power transformer that you commonly see in a linear or conventional power supply. In the case of the switching regulator power supply, we can use a much smaller transformer with a core made of a material called ferrite. The reason we can get away with that is that the switching regulator power supply works at a much higher frequency than the 60 cycle operating frequency of a normal linear power supply. The frequency of a switching regulator power supply is around 40 kilohertz, or 40,000 cycles per second. And that's a big advantage because we can now use this tiny little power transformer instead of the much larger, heavier, and more expensive iron core transformer that we find in a conventional or linear power supply. But we know that a transformer is strictly an AC device. And we know that the power supply that we've made so far, the high voltage supply, is plus 150 volts DC and minus 150 volts DC. How do we use this DC power supply to drive an AC transformer? Well, remember the switching transistors. The switching transistors are alternately passing the plus 150 and the minus 150 to the power transformer. First, one transistor switches on and sends the plus 150 to the transformer. Then that transistor turns off and the other transistor turns on, sending the minus 150 to the transformer. Since first we get plus 150 and then we get minus 150, well, that's alternating current, isn't it? and that's how we get our AC input to the power transformer. To rectify the output of the transformer, we use a very special kind of a diode, and that diode is mounted here on this other heat sink. And again, there's a clamp that holds it on. I'll pull this clamp off so we can take a close look at this special high-speed diode. It's called a Schottky diode, and it comes in a package that looks very much like a transistor package. Here's the dual diode itself. This special high-speed diode takes the AC output from the transformer and rectifies it, turning it into direct current. Well, after it's been rectified, naturally it has to be filtered. This is the same whether it's in a conventional linear supply or in this switching regulator supply. But in order to filter the very high frequency AC output of the switching regulator supply, we have to add a couple of other very special components. One is this. Do you see these donut-shaped devices? Well, they're known as toroid coils or toroid chokes, and they're very important. They have a very special and unique property that we use to our advantage in the switching regulator power supply. The choke acts to cut off any AC interference that might come out, but allows the DC to pass through unaffected. It chokes off the AC interference, hence they're called chokes. After passing through the choke, the DC output of the power supply is filtered by filter capacitors. And you'll always see a group of filter capacitors, low voltage capacitors, clustered in one corner of the power supply. This is where the final output filtering takes place. Well, these capacitors have to be very special types of capacitors. They're known as low ESR capacitors. Well, without getting into too much detail, ESR stands for equivalent series resistance. A low ESR capacitor has the ability to filter out the very high frequency ripple or interference that might be coming out of the output of the power supply. A normal capacitor will not last in a switching regulator power supply. So when you replace output filter capacitors, you need to replace them with low ESR capacitors. Well, there's really only a few more things that we need to look at in this power supply. Let's go back to the switching transistors. Remember, there's a pair of transistors mounted on a heatsink that are switching rapidly on and off at 40,000 cycles per second. What controls these transistors? Well, it's simple. There's an integrated circuit here that tells the transistors when to turn on and off. This integrated circuit, which is the same in just about every power supply, is in itself powered by a separate power supply on the switching regulator board itself. Look, over here on the other side of the switching regulator power supply, you'll see a small transformer. This transformer gets its input from the 115 volts AC and gives us an output which is rectified by a pair of diodes and filtered by this filter capacitor. This creates a power supply of around 16 volts DC, which is then used to power the integrated circuit itself. Also, adjacent to the switching transistors, you will see a pair of diodes. These diodes, which are known as the clamping diodes, are kind of a protection device that keeps the transistors from blowing out. In addition to the plus 5 volt output from the power supply, remember there's also a plus 12 volt output and a minus 5 volt output. Well, we use an additional pair of diodes for each of these outputs. Right here are the 12 volt diodes. And right next to them are the diodes for the minus 5 volt output. Naturally, there are output filter capacitors for these two supplies as well. In general, they use a pair of 3300 microfarad capacitors for the plus 5 volt output, a 2200 or a 1000 microfarad capacitor for the plus 12 volt output, and a 1000 microfarad for the minus 5 volt output. As part of the filter circuit for the minus 5 volt output, instead of a toroid choke, you may see a conventional coil like this one. It looks a lot like a capacitor, so don't get confused. Well, now that we know how the power supply works, let's take a look and see how it fails. It really doesn't make very much difference if you understand how the power supply works, as long as you understand what causes it to fail. Generally, we can break the failures down into two different types of failures. One type blows the fuse, and the other type doesn't. They both seem to be just as common. You see just as many failures that blow the fuse as failures that do not blow the fuse. Let's take a look at the failures that blow the fuse first. And the most common failure is failure of the switching power transistors themselves. Remember the two switching transistors that reside on one of the heat sinks. When these fail, they always blow the fuse. When the switching transistors fail, they short collector to emitter and blow the main power fuse. When you test the transistors in circuit, that is, when you test them as they're soldered on the board, they will not test properly, even if they're good. For instance, if you test them from base to emitter, they will always appear to be shorted in circuit. That's because of these two small driver transformers. These transformers are used to drive the switching transistors themselves. When you test the transistors in circuit, you actually don't have to do the complete transistor test. If you find that the fuse is blown, one of the first things you want to do is check these two transistors. But all you have to do is check them from collector to emitter. When you check them from collector to emitter, if they're bad, they will always show as a short circuit. Another common failure that will blow the fuse is failure of the clamping diodes. Remember, the clamping diodes are these two small diodes that are right next to the transistors themselves. When these clamping diodes fail, they also short circuit and blow the fuse. Another failure that will blow the fuse in the power supply is failure of the bridge rectifier. When the bridge rectifier fails, it short circuits and blows the fuse. Whenever you work on a power supply that has a blown fuse, make absolutely certain that you check all of these components. Check the two switching transistors, check the clamping diodes, and check the bridge rectifier. If you do find that you have one or two bad transistors, make absolutely certain that when you replace them both. Now, normally I would never suggest that you replace a component that tests good, but in the switching regulator power supply, it's very important that both of the switching transistors be absolutely identical. Specifically, they must have the same gain. Remember, the gain of a transistor is the transistor's ability to amplify. If you have transistors that have mismatched gain, they'll just blow right back out again. A power supply failure that does not blow the fuse is very easy to diagnose. Generally, there's only a couple of things that can cause that. And one of them is failure of one of the two diodes that are for the plus 12 volt power supply. These power supplies have something known as an overcurrent protection system built right in. The overcurrent protection system will shut off the power supply just like that when the output is short-circuited. Well, when one of the plus 12 volt diodes fail, it causes the overcurrent protection system to activate. As a result, you get no output from the power supply. You still have your 115 volts in, but nothing out on the plus 5, plus 12, or minus 5 volt supply. Remember, the overcurrent protection system, or OCP, has completely shut down the entire power supply. So even though your problem is simply one of the plus 12 volt diodes that has failed, the entire power supply will be shut down and you will get no output from any of the outputs, plus 5, minus 5, or plus 12. Likewise, when one of the minus 5 volt diodes fails, you will also get the exact same symptom. When one of the minus 5 volt diodes fail, again, it activates the overcurrent protection system and you get no output. Well, now let's take a look at the filter capacitors. Remember, the output filter capacitors are the last filtering stage in the power supply. When the output filter capacitors fail, they usually look bad. You'll see them swollen or cracked or leaking all over the board. Anytime you have a capacitor that looks like it's all swollen up or is leaking, or if the plastic covering on the capacitor has shrunken down, that capacitor is bad and must be replaced. As a matter of fact, when I'm working on a switching regulator power supply, I generally replace all of the output filter capacitors regardless. I do this because as replacement capacitors, I make certain that I use low ESR capacitors. Remember, we talked about those earlier. The low ESR capacitors are special capacitors that are very effective in removing this very high frequency ripple or high frequency noise output from the switching regulator power supply. Most of these power supplies do not have low ESR capacitors installed stock. This one happens to be made by Peter Chow himself, and Peter Chow does use low ESR capacitors in his power supplies. Again, we'll be talking more about replacement components later on toward the end of this lesson, and I'll give you a source for low ESR capacitors. If you are not replacing all the output filter capacitors, it's very important that you test them. To test the capacitors adequately, you do need to use a capacitor meter. Using the capacitor meter is very simple. All you have to do is unsolder the capacitor from the board. You must remove it from the board to test it, and connect it to the capacitor meter. The capacitor meter will tell you if it's good or bad. If the capacitor meter shows you the same number of microfarads as is written on the outside of the capacitor itself, then the capacitor is good. However, if the capacitor meter shows you a lower reading than what the capacitor is supposed to be, then the capacitor is defective and should be replaced. Well, there's really not much else that ever fails in the switching regulator power supply. Occasionally, you will see failure of the integrated circuit itself. The integrated circuit itself cannot be tested directly. In order to test the integrated circuit, which again I rarely have to do, I've taken a power supply that's working and removed the integrated circuit and replaced it with a socket. When I want to test an integrated circuit, all I do is unsolder it from the power supply that I'm working on and plug it into my test power supply. I turn on the test power supply, and if it works, the integrated circuit is good. You may see several different numbers for the integrated circuit that we use in these power supplies, but they're actually all identical and they're all interchangeable. The most common one is the type 494. And you may see different two-letter prefixes on this part number. It may be TL494 or UP494 or GL494. As long as it says 494 in it, it's the same. It's a 494, obviously. Other part numbers will be MB3759 or IR3M02. All of these integrated circuits are identical and they're all interchangeable. If you're looking for an over-the-counter replacement, an ECG 1729 will do the trick. Well, that's really about all there is to it. If you've tested those components and replaced any that were bad, and the power supply still isn't operating properly, well, there's really not very much left. You may find one or two other small transistors that you need to test, and there are a few diodes and some resistors that you need to check as well. Quite frankly, I rarely find any of these to be bad. Well, once you've found the bad components, you need to get replacement parts. And replacement parts can be a big problem if you don't know where to look. Fortunately, I've done some research and I found some very inexpensive sources for replacement components. Specifically, there are two different types of replacement components that you need to get. One is the transistors themselves. The switching transistors are type 2SC3039. And for a while, I was paying $8 a piece for these transistors, but I've now found them for 90 cents a piece. The source where I get them is JC Electronics. The switching transistors can also be obtained from worldwide component distributors. The low ESR capacitors are available from a company known as TTI. TTI happens to be the nation's largest distributor of passive components like capacitors and resistors. And it's really great. They have a toll-free number that's easy to remember. It's 1-800-CALL-TTI. The capacitors that you want to order are 3,300 microfarads at 16 volts. Remember, you need a pair of those for the 5-volt output. I use 2,200 microfarads at 25 volts for the plus 12-volt output. And I use that regardless of what is original equipment in the power supply. Even if there's a 1,000 microfarad in there, I replace it with a 2,200. Remember, in a power supply, you can always use a larger filter capacitor. So that's what I use. And for the minus 5-volt supply, I use 1,000 microfarads at 16 volts. Remember, you need to order low ESR capacitors. They're manufactured by a company known as Nichicon, N-I-C-H-C-O-N. And make certain that you order capacitors that have radial leads. Capacitors with radial leads have the leads coming out the bottom of the capacitor. They're also known as PC mount, or printed circuit board mount.
There's a few more things that I want to review as far as the power supply is concerned. First of all, let's go back to the problem where the fuse is blowing. It's blowing the fuse. Remember, there's only 3 things that blow the fuse in the power supply. The most likely thing is those switching transistors. Absolutely the most likely thing. Can everybody see what I'm talking about? Can you see where the 2 transistors mounted on the heat sink? Really important. Now, here's the really cool shortcut for checking those transistors. When you want to check those transistors, you do not have to make the complete transistor test. It just takes a couple of seconds to check the transistors. Does anybody have a blown fuse? Doug, did you say you had a blown fuse? Yours is blown? Dan? No. Who had a blown fuse? Somebody did. Wayne has a blown fuse. All right, let's go over here. Let's see if we can figure out what blew the fuse in Wayne's power supply. The first thing you have to suspect is the switching transistors. Now remember, these are 2 transistors in TO220 packages. So remember the way the TO220 package is set up. It's in alphabetical order from left to right. B, C, E. Well, remember, the main switch in a transistor is from the collector to emitter, and that's the only place you have to check. You set your meter to the diode test scale. And of course, you do this from the bottom of the board because you can't get to the legs from the top. So you look, see where the transistor is, turn it upside down, and go from the center leg to the right-hand leg. And all I'm doing is just putting 1 meter lead, doesn't matter which one, on the collector, which is on the center, 1 on the emitter. That one's open, so that's good. You'll either get an open reading or a junction drop, like that. You'll either get open or a junction drop. Let me try the other one. Oh, the other one's good too. And neither of these things is shorted. Very often they are, and all you have to do is that, you'll find that they're shorted. So, that being the case, I'm not sure why his fuse is blown. We'll have to try to figure that out. The next thing you want to do, first of all, does that make sense? Can you see what I'm talking about? All you have to do is check the transistor from collector to emitter. Do you understand what I'm talking about? The next thing we want to do, are you cool on that, Mark? Cool, all right. The next thing you want to do is check the clamping diodes. Check the clamping diodes. And let's see if we can find these things. The clamping diodes are always right in front of the transistors or immediately behind, depending on the model. Do you see your 2 clamping diodes right there? You see yours, Dan?
Yeah.
Right in there? Okay. You got yours, Tony?
Yeah.
Seeing those 2 right there. You see them, Dustin?
Yeah, right here.
Let me see them from the top. I just want you to point them out from the top. Okay, right.
These 2?
Correct. Yeah, those 2 there. Or in this one, they're standing upright. See that? Doug, you see yours?
These 2 right here.
Correct. And on this one, I think they're behind it. See how they're behind it on that?
Oh, yeah. Okay.
All right. You got them there? All right. Now, here's what these guys are for. These are called clamping diodes. These are called the clamping diodes. They are protection diodes. They're there to protect the transistor. Without clamping diodes, those transistors would blow right out. And I don't want to get into it in any more detail than that. It's not important to know any more detail than that. Now, where they're connected in the circuit is here. They're connected, each transistor has a clamping diode, and it's connected right between the collector and the emitter. When you test the transistor, when you check it from collector to emitter, if the transistor is good, if the transistor tests good, the clamping diode is also good. You have tested them both at the same time. So that's a cool shortcut. In other words, if I do what I just did on Wayne's power supply, where I check across the transistor from collector to emitter, and I find the transistor is good, the clamping diode is also good. I don't spend any more time checking the clamping diodes. So that saves you a couple minutes or a minute right there. Okay? Everybody with me on that? Okay. But what this also means is this, very important. There's a reasonable chance that your clamping diode is the thing that's shorted. The transistor might be shorted from collector to emitter inside. Or the clamping diode might be shorted, or they both might be bad. So listen carefully to what I'm saying here. When you check the transistor from collector to emitter, if you find it to be bad, the meter will show a short circuit. You will see 0.00 something on the meter. 0.000, 0.001, 0.002, something like that. Something obviously dead short, just like the diode when I showed you what a shorted diode looks like. Those diodes actually came out of a switching regulator power supply. When I demonstrated these bad diodes here, these should look pretty familiar to you because you have one, a similar type of diode that I gave to you. This came out of a switching regulator power supply. When the parts go bad, you see like that, 0.000. See on the meter? If we zoom up here, and if I put my meter leads across it, 0.000, it shows a dead short. All right? When I'm checking the clamping diode, when I'm checking the transistor from collector to emitter, if the meter shows a dead short, the transistor is shorted, or the clamping diode is shorted, or they are both shorted. So this is very important. Assume the transistor to be shorted, because that's usually what it is. When you pull the transistor out, that is when you unsolder it and remove it, make certain that you double check the transistor out of circuit between collector and emitter to see if it's shorted. You don't have to do the complete transistor test, just collector to emitter, see if it's shorted. And this is important, also check the clamping diode. When the transistor is out, check the clamping diode. And you can do it, at the same place, at the holes where the collector and emitter used to be. You've pulled the transistor out. You can just go on those same 2 points on your board and check it again. If you still have a short there, the diode is also bad. When you pull the transistor out of circuit, double check the transistor. If you find it to be good, the clamping diode is your only problem. Put the transistor back in and take the diode out and replace it. On the other hand, you may find the transistor and the clamping diode are both bad. And this is why people get frustrated when they're working on power supplies. When people are working on switching regulator power supplies, a lot of people will try to tell you, well, they're like disposable. They're not worth fixing. Well, the reason they say that is that they get confused. And here's what will happen. Someone will get to the power supply. They'll find that the fuse is blown. They'll find that the transistor is shorted from collector to emitter. They'll change the transistors, they'll put in a new fuse, and of course, remember we discussed the fuse is soldered in place. So that's a hassle. They change the fuse, as soon as they fire it back up, the fuse blows again, immediately. And now they're really pissed off, they throw the thing against the wall, or step on it, or throw it away, or whatever. So we're not going to make that mistake. So again, one more time. You get to the power supply, the fuse is blown. First thing you do, turn the board over, check it from collector to emitter. Beep, it's shorted. Unsolder, remove the transistor. When you get the transistor out, double check it, see if it's good or bad. And while it's out, double check the clamping diode, make sure that it is good, and if it's bad, of course, replace it. Everybody with me? That'll save you a lot of headaches right there, because that really confuses people. And we'll talk a little bit more about what the parts are, where to get them, just a sec. There's one more thing that can cause the fuse to blow, and that is the bridge rectifier, or the 4 diodes, depending on what you have in your particular power supply. Now, a lot of times what happens is people find the fuse is blown in a power supply, and before they try finding out which parts are bad, they simply replace the fuse, only to watch it blow again. That will take out the bridge rectifier if you do that. If you get to a power supply with a blown fuse like that, like this one is, like Wayne's is, we need to check some things, and what we need to check is the transistors, like I just did, and that checked the clamping diodes, and we need to check the bridge rectifier. Now, I seriously doubt that the bridge is bad in this one, because it's very unusual for the bridge to fail by itself. Usually the bridge fails as a result of something else failing, but let's check the bridge rectifier and see if it's good or bad. And again, since we have a blown fuse in here, what I'm looking for is a short circuit, basically. Luckily for us, when the parts go bad, they almost always short circuit. So let's check. Here's one of the diodes. I see a junction drop. It's not shorted. There's another diode I see open. It's not shorted. There's another one, junction drop. Another one open, or junction drop, depending on which way I put my leads. No. The bridge rectifier seems perfectly good in this one. Why the fuse is blown, I don't know. Probably in this case, we'll be able to put the new fuse in and have it work. There's a couple of other diodes here. I'm going to quickly check, and I'll tell you what I'm going to do. I'm doing it in just a second. Let me just see something here. Yeah, that's good, as I expected. So it's that. Yeah, this one, I really have no idea why the fuse is blown on this one. It does appear to be blown, and I should probably double check it with my meter. Yeah, it's definitely blown. And yet, I don't really see anything in particular that might cause that to blow. So at this point, I might consider changing it. This particular power supply does have one cap that I probably want to change, and I'll walk around with this so you can take a look at it, and you'll see that the plastic covering is starting to shrink on this. You see on this one compared to that one, do you see how it's starting to shrink?
Yeah.
That should not blow the fuse generally, but I'm going to replace it anyway, because as long as we got, or somebody is anyway, as long as we've got them here, we might as well change it. See? That's the kind of stuff that you're looking for. See right here, see how this one here is a lot more shrunk. See this guy? See how the covering shrunk on that one compared to that one, right? For you folks at home, see if you look at those capacitors right there, you see how that one's shrunk and a lot more of the top is exposed than that one, which you probably really can't see. So in fact, here, look at it. Look at it up close. See how this capacitor, the top is shrunk, and this one is more covered. And that's what you're looking for. Thank you. Thank you very much. Okay. So anyway, we'll change the fuse in that, and then we'll see what happens. Or somebody will change the fuse in it anyway. Anyway, so the point is here: when you find that the fuse is blown, make certain that you check all those things. All 3 of those things, very important: transistors, clamping diodes, bridge rectifier. And I screw myself up all the time by forgetting to check the bridge rectifier. I find bad transistors or bad clamping diodes. If I change the fuse, I get all excited. I plug the dang thing in, pops the fuse again. I go, oh, forgot to check it. I could have had a V8. Forgot to check the bridge rectifier. And don't forget, when the fuse is blown, there's a good chance that that resistor will now be open. That little 1.5 ohm resistor that's on the AC input. When the fuse is blown, there's a really good chance that that resistor will open circuit. If you can just think to throw a meter across it and check, make sure that it's good whenever you change the fuse, check that thing at the same time. It'll save you a little time having to hook it up, find it's not working, and then find the resistor and so on. Now these resistors. Oh, wait a minute. Just for those of you in the home audience here, let me show you this up close. It's this white resistor right here. It's 1.5 ohms. When the fuse blows, there's a really good chance that that resistor will open circuit. That resistor right there. Your reads 1.9. Touch your 2 meter leads together. What do you get on the reading when you just touch your leads together? 0.3. So there's your difference with 0.1 difference. So that's okay. When it's bad, it's open completely. Right. Now, these little resistors, actually you can get at Radio Shack, you can get half ohm resistors. They're actually 0.47 ohms. They're available at Radio Shack. That's okay to use as a substitute. That's fine. As a matter of fact, if you get stuck and it's an emergency and you got to fix a power supply, you can replace that with a piece of wire. You don't really have to have that in there. It's good engineering practice for it to be in there, but if it ain't in there, that's okay. It'll still work perfectly okay. You may shorten the life expectancy of the power supply somewhat, but quite frankly, I doubt it. I think it's really perfectly okay not to have that in there. So if the fuse is blown, that's basically it. In fact, there's only one other thing that I've ever seen blow the fuse, and that's this blue capacitor. We were talking about the AC line filter earlier, how we have the AC line filter coil thing, and then one of these capacitors that's right nearby it. I have occasionally seen this capacitor be the problem. This blue, oh, stop that. I've seen this blue capacitor right here short circuit a couple of times. And, in fact, we should check that on Wayne's power supply. Maybe that's what's wrong with his. On this power supply right here, because his fuse is blown, but the transistors are good, the clamping diodes are good, and the bridge rectifier is good. Oh, wouldn't that be something if that's what it was? Let's take a look at it. It's something that rarely happens. Let's just see if it's shorted or not. Be kind of bitching if it was, in a way. Let's see. Son of a bitch! It is shorted, 0.000.
Number 2.
Yeah, I haven't seen this very often at all. How about that? That's very interesting. Maybe I should add that to the list. It's definitely shorted. I'm going across. Oh, unless I was reading across the fuse. Wait a minute. The fuse is open, isn't it? Fuse is bad. I already checked that. No, it's bad. It's bad. This capacitor is this little blue capacitor here as part of the AC line filter. It's going right across the power line, and it's definitely shorted.
Check that in diode setting.
No, on ohms. Well, it is on the diode check setting now, and obviously it's shorted. But you would probably check it on ohms, really, 200 ohms, and it should be open. You should not see a short circuit there.
How do you see it go across the short with the diode setting?
Well, the diode setting and the low ohm setting are basically the same. It just interprets the display a little differently. Actually, I shouldn't say that, because the difference is in the diode setting it puts out about 2.5 volts. In the ohm setting it only puts out 0.4 volts. It does that intentionally so that when you're measuring resistance with your meter, it ignores semiconductors. It's putting out less than 0.7, so it completely ignores the semiconductors. It's like they're invisible to the meter, which is a really nice thing, really. So that's good. I feel better now. Now I know what's wrong with this one. And in fact, before we fix this one, I'm gonna make sure that since there's only 7 of us here, we each might as well see every power supply that has a problem in it and see what's wrong with it. And I'll pass this around later on so that we can take a look at it. All right. So when you get to a power supply and you find that the fuse is blown, check, I guess, these 4 things. Check the transistors, the clamping diodes, the bridge rectifier, and if all of those things are good, then check that blue, well, it's not always blue, check that capacitor that's on the AC, right across the AC input. Does that make sense to everybody? Anyway. All right, let's get back to this so we can fix some of these things. If the fuse is not blown, you really have a pretty simple problem here most of the time. And there's really only a couple of things that commonly do that. The plus 12 volt output diodes and the minus 5 volt output diodes. So let's see if we can find those guys. Where's that power supply, Wayne's power supply that I was messing with? The one with the shorted capacitor. Is this the one?
Yeah.
Okay. If you look at your power supply, you'll see like a pair of 3 amp diodes and a pair of 1 amp size diodes, like the diodes that I gave you in the class. The 3 amp size, the larger ones, and the 1 amp size. The 3 amp size are for the plus 12 volts. And right next to it, the 1 amp size over there, that's for the minus 5. We've got plus 12 and minus 5. Anybody not see theirs? Dustin, you see yours clearly? You know what I'm talking about, Tony?
Right over here, right?
Yeah, your plus 12s are there, and I guess your minus 5s are those two right in there. See those? Okay. Yeah, yours are standing up on a heat sink.
Right.
Right, that's for the plus 12.
And the 5s.
And the minus 5s are down in there, yeah. Show those to Mark.
These are here.
Correct, yours are all just side by side there.
A little bit there. See me?
See, like that. And then yours right here are like the plus 12 and the minus 5 are right there. Okay. Everybody see where we are right now? All right. Remember from the videotape, these things have a built-in overcurrent protection system, OCP, overcurrent protection. When the output diodes fail, the plus 12 or the minus 5, if they short circuit, it shuts off the whole power supply. And it shuts off the entire power supply. You get no output from any of the outputs. All right, now, these diodes do not test good in circuit. When you go to check these diodes in circuit, they do not test good. For instance, when you check them in circuit, what you'll probably see is, if I check it from anode to cathode, in circuit, you usually see about 0.1 on this meter. It depends on the power supply. This one says about 0.2. It says 0.197, really. I'm going right across the 12 volt diode. From one side to the other, I get 0.197, and I get the same in both directions. On the minus 5 volt diode, I get the same thing both directions. I'll either get that or 0.099 or 0.1 or something that seems bad, doesn't it? It seems incredibly low, it seems bad. That is actually good. When the diode fails, you read 0.00 something. Who's got that shorted diode? All right. So I get to this power supply and I say, oh, is the fuse blown? No, it isn't. Okay, fuse is not blown. I'm not checking the transistors. I'm not checking the clamping diode. I'm not checking the bridge rectifier. I'm not checking that 1.5 ohm resistor. I don't care anything about those. If those guys failed, other than the 1 ohm resistor, it would blow the fuse, right? So I'm going right for these diodes. And I go right across the diodes, the plus 12 volt diodes, and the meter says 0.196. Those are okay. That one's okay. That one's okay. I don't have to bother going both directions because I'll get the same both ways. Let's check the minus 5 volt diodes. Holy bejesus, 0.000. Right across that, and across the other one as well, 0.000. So that's what's wrong with this one. Total time to diagnose it, look at the fuse, bam, bam, less than 1 minute, obviously, way less than 1 minute. And that's my problem. Now, what a lot of people will do when they want to check these diodes is that they will laboriously unsolder and lift one end of the diode to get it out of circuit so they can check it properly. Don't bother. If it says 0.00 something, it's bad. If it says anything else, it's good. That's the bottom line. Now, when you check, and I think in this case, because of the discoloration of these capacitors, instead of being real bright orange, they're starting to get brown. I think that maybe that is what caused the diode to fail. Oh, one of them's even busted in half. One of these minus 5 volt diodes is completely broken in half. That's interesting. Let's see some. Well, I must have just done it while I was testing it. The other one shorted. How interesting. So obviously we'll have to change them both. Now, when one of the diodes is shorted, they both do appear to be shorted in circuit. Really, probably only one of them is bad. In this case, they are both bad, and occasionally they both fail. But when you check across either the plus 12, the big diodes, or the minus 5, the little ones, if either one is shorted, they will both appear to be shorted. So now you got a 50-50 chance. Unsolder and lift one leg of one of the diodes. You got a 50-50 chance of getting the right one. If that's the good one, put it back down and take out the other one. Man, that's simple. When I get to a power supply without a blown fuse, the fuse is okay, I just whip right on those diodes. Most of the time it's a plus 12 or a minus 5 volt diode that is bad. It's very common. Very, very, very common. There is a remote possibility that the plus 5 volt diode is bad. The plus 5 volt diode is the thing that lives on the other heat sink. You know, one of the heat sinks has the 2 transistors on it. The other heat sink has the special plus 5 volt diode. It's called a Schottky diode. S-H-O-T-T-K-E-Y. It's called a Schottky diode, named after the guy that invented it. It looks just like a transistor, doesn't it? I don't know if you took that clamp off or not, but what it looks like is this. It's in a TO218 package. It's TO218. It's kind of a larger version of the TO220 package, basically. And what this is 2 diodes in here. Inside this thing, there are 2 diodes. Their cathodes are tied together, and they go to the center leg. I have rarely seen this fail, but I saw one fail, in fact, in the last class that we did. And again, when it fails, what you're looking for is that, 0.00 something. Turn your power supply over upside down and check this diode. And the way you check it is, it's like half a bridge rectifier. Put one lead on the center and go to the other leg. Then move to the other leg, from the center to the other leg. And what you're doing is checking both the diodes. You will see that it is incredibly low. You'll probably see something on your meter like 0.05 or something like that, something incredibly low. Try that. What do you see? What did you get, Tony? Did you try it? What, 0.05? Yeah, 0.05. So you would go, whoa, 0.05, that's bad. That's way bad. But because it's in circuit, that's a good reading, actually. When it's bad, you see 0.00. If it really is bad, it'll say 0.00 something. So that's a really cool shortcut. Like on this one, I get, 0.09 on this one. Depends on the model.
When it's bad, you'll see what again? Point something.
The cool thing about the switching power supply is that it's yelling at you, telling you which parts are bad. Because when they go bad, they do that. Or they usually look, if it's capacitor, it looks bad. Does this make sense? So far, so good? Okay. Yeah.
I touched it, the board itself.
The foil pulled up?
It up a little bit.
Yeah, that doesn't surprise me, as hot as it's gotten.
Well, it's broken.
Yeah. Oh, yeah, it's broken. Well, we'll fix that. There's no problem there. Unless the leg is busted.
The leg's busted.
Oh, the leg's busted on the device.
Right.
Oh, it certainly is. It's busted right off, yeah.
Well, now it's reading like 38 point something.
Yeah, that's bad. We're gonna want to replace that, just because the connection is electrically broken, so we need to replace that. Does this make sense so far? Okay. Now, regardless of whether the fuse is blown or not, you always look at the filter capacitors. Remember, the filter capacitors are the ones that are in one corner of the board here, And also, I've seen this capacitor fail a lot. One of them in this room is bad because you showed it to me. This capacitor here that filters this makes a 16-volt power supply that powers the chip. Over here on this side, I've seen this capacitor also go bad. This capacitor right here. Remember, this is the power supply that powers the integrated circuit. This transformer here and the capacitor and these two diodes form a power supply that actually, it only powers this integrated circuit. That's all it does. And I've seen this cap also fail quite often. Well, not quite often. I would say sometimes, I guess. How's that for a non-specific term? Who's that one's okay though.
That's the one you're talking about.
Yeah, that's the one I'm talking about. Who has the bad one?
Not very bad, but it's bad.
Yeah, oh, it's definitely bad. In fact, there was a little bit of white electrolyte coming out of it that I saw in the car, and I accidentally knocked it off. But if you look at this one, you can see that it's definitely bulged. If it's bulged, it's bad. See this one right here? See this guy, Wayne, how it's slightly bulged up?
Yeah.
And in fact, we're going to probably want to change all these, to be honest with you. See, this one is slightly bulged. Not by a lot, but it's enough to tell you that it's bad. These diodes, the plus 12 and the minus 5 volt diodes, are not standard diodes. Let me see if I can. Hang on one second here. I'm going to find something. The plus 12, the minus 5, and of course this plus 5 volt diode, these are not standard diodes. They're special high-speed diodes. Like I said, this one's called a Schottky diode. The other one's maybe just called fast switching diodes or fast recovery diodes. And you cannot use regular diodes. Like the two diodes that I gave you, they physically look like they would work okay, and their specifications are even okay, voltage and current-wise, but they can't respond to the real fast switching action of the power supply. You need to get special high-speed diodes for these things. I believe Worldwide Component Distributors has these diodes. And typical part numbers are like for the plus 12 volt diodes are FR, standing for fast recovery. FR 1004, I think, is the part number. Let me just double check that. I don't have a reference to that number. It's the one that I have is PXPR 3004. The minus 5 volt diodes are PXPR 1504. The clamping diodes also have to be high-speed diodes, PXPR 1507. I think that Worldwide Component Distributors carries these things, but there is one place that you can get all of these parts. You can get replacement parts for these power supplies from Imperial International. They are the people that sell the Peter Chow power supply. Imperial International. And they're a big parts house, like Wacko, whatever you call them. Imperial International. No, they're not. So I'm going to put this number on the board right here. They have a California office and a New Jersey office. The California office is area code 800-423-2753. They carry the capacitors for these things. They carry, the power supply itself. They carry you know, all the replacement parts, the diodes, the transistors, all that kind of stuff. If you happen to be in the New Jersey or greater New York area, fixing a game, 800-526-6261. So there you go. Imperial International. They have, like I said, they have all the parts. They have all the replacement parts. They have the transistors. They have the diodes. They have all that kind of stuff. And if you are going to buy a lot of replacement parts, you really want to go like get the transistors and the semiconductors at worldwide component distributors. JC Electronics is actually out of business. Oh, I never mentioned JC Electronics to you guys. So they're out of business anyway, so it doesn't make any difference. Worldwide component distributors, the address is in the back in your blue book on page 82. Because the switching transistors are only $1 a piece from them, so that's very cheap. You do have to buy 100 at a time. Wait a minute, maybe I'm wrong about that. No, I'm wrong. They only have like a $25 or a $50 minimum. It's real easy to come up with that. And so getting replacement parts shouldn't be a problem for that. Everybody with me so far? Okay, well that's really about it for this Peter Chow style power supply. There is another kind of power supply that we use, very common in games. It's called the Hytron power supply. A Hytron power supply is an excellent power supply. It's a really super high quality power supply. I did a power supply review where I got samples of every kind of power supply that there are, and I checked them all out for different conditions and how they were constructed and electrical noise and all that kind of stuff. And the Hytron power supply came out right absolutely on the top. It was absolutely the best. However, they're a lot more expensive. Where you can get a Peter Chow style power supply for $30, they're $46 or something like that for a Hytron. So it really, it's up to you whether you get those kind or not. This is a Hytron here. Quite frankly, they're a lot more expensive. I'm going to tell you right now the one thing that I have found goes wrong with this thing more than anything else. In fact, 90% of the time it's all that's wrong with it. However, where the Peter Chow power supply is real easy to troubleshoot, this really isn't. Fortunately, nothing ever goes wrong with it other than this one thing, which is really nice. And if I fix this one thing or I replace this one thing, which is a capacitor, and it doesn't fix it, and it's not something obvious like a shorted transistor or something like that, or other capacitor failures, then I probably can't fix it, to be honest with you. But there's one real common failure, and it's failure of capacitor C10. On the Hytron power supply, the first thing you do is you open it up and replace capacitor C10. C10, the original one, is 220 microfarads, 16 volts. You can replace it with anything up to like 1,000 microfarads. And of course the voltage, you know, remember in a cap you can always go as high as you want in voltage. Now that capacitor is right here. It's this little cap right here. Here's in this power supply there's one main switching transistor, and I'll walk around and show this to you. Just one main switching transistor, and there is a capacitor right next to it here that goes bad. Let me just walk around and show this to you here. It's this cap right here, C10. Yeah, it's a little bulgy. Very often it doesn't look bad though. Very often it looks perfectly okay. But every time we pull them out and test them, it's like completely open. There ain't no real capacitor inside anymore. It's just two wires going into an empty shell, basically. This cap right here. That guy right there, C10. The reason that this thing fails, the reason this capacitor fails is that it's mounted right above a resistor. This is the way you see the power supply. This is the way normally the power supply sits. It's mounted above this high wattage resistor right here. And the heat travels up from this resistor and dries out the capacitor. Remember, that's what causes capacitors to fail. They dry out. Well, that's kind of dumb engineering in a way. Although if the power supply was mounted like this, of course, it wouldn't be a problem. The heat would just come right up. But because it's really mounted like this, all the heat rises and dries out that capacitor. That's why it's such a common problem. In fact, if they hadn't done that, maybe this thing would last for, years and years and years. But these will generally last 2-3 years without failing. And the symptom is, and the symptom comes on a little at a time, and for those of you that have arcades, maybe you'll see it happen. You turn on the game, and it doesn't come up right away. So you turn on the game, and it just sits there, and then 1 minute later, or 2 minutes, or 5 or 10, all of a sudden, bing, the game comes on by itself. That's that capacitor going bad. Or it just never fires up at all. It just eventually gets so bad that the power supply never fires up at all.
I know we can check on one game.
Sure, it's real common. Well, now we're going to fix some power supplies. When we fix the power supplies, I don't want you plugging in your power supplies up here. When you think you're ready to test the power supply, you're going to bring it up here in the front, and we're going to check it together here at the front desk. And what we'll do when we bring it up here is we are going to put a resistor across the power supply. In order to check the power supply properly, you must put a load on it. So I've got this 1 ohm resistor, a 1 ohm 25 watt resistor, that we're going to put across the power supply from 5 volts to ground. It's what we commonly call a dummy load. In other words, we have to draw some current out of the power supply to really test it properly. It may work perfectly fine with no load on it, but when you put a load on it, it may crap out. Or, for instance, the Hytron power supply, many of them don't even fire up without a load. If you don't put a load on many of the Hytron supplies, it will click. It'll just go click, 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 click. This relay will start opening and closing as its protection system keeps kicking in. And a lot of power supplies, like I had a guy bring up a power supply to me in North Carolina and say, it's broke. I've checked everything seems okay, it's broke. And I fired it up in the front, and nothing was coming out of it. I clipped the load across it, and it works fine under load. It just doesn't work without a load. So when you bring it up here, we're going to put a load on it so that we can test it properly. And when you do work on your power supply in the shop, you should do the same thing. Now, we could use a logic board as a load, but suppose the power supply is bad and it's putting out 8 or 10 volts instead of 5. Maybe you'll blow your logic board. You can't blow a resistor like that.
What size resistor?
It's a 1 ohm 25 watt resistor, and in your blue book, if you turn in your blue book to page 45, you see the power supply tester that I made. It's not very sophisticated. It's just a piece of wood with a bunch of resistors screwed to it, really. That's all this is, just like a piece of wood with a bunch of resistors screwed on it. Resistors right here. If you turn the page, you see the schematic diagram for it, and all I have is, I have a bunch of 5 ohm resistors in parallel, actually. You don't really have to do this. A 1 ohm 25 watt resistor will be perfectly okay. I did this because it does get quite warm, and I don't really want one resistor that's going to get super hot. I spread the heat out among 5 or 6 resistors this way, which is kind of nice. You don't really have to do this. You just need to clip a 1 ohm resistor from 5 volts to ground. That draws 5 amps. That's enough to test it. So that's what we're going to do up here. So here's what you're going to do. Go through your power supply, check it out, find any parts that you think are bad. When you get the bad parts, take them out, bring them up here. I will trade you a good part for a bad part. Then you put in the good parts when you're ready to test the power supply, or like if you check the power supply and you can't find nothing wrong with it, bring it up here, we'll test it out, and we'll see if it's good or bad. Okie doke? Let's go.